There is jump if not equal instruction, but there is also opposite instruction, jump if equal. If I change this instruction to jump if equal, it should do what I want, right? Let's talk about memory. We already mentioned some crucial parts of the computer as a memory, language, and microprocessor from the big picture. But today let's take a deeper look to this essential part which allows you to communicate with computer, to actually exchange the data and program. Last time we talked about the language more deeply, like what they are, what categories they have, what they are used for. Well, you already know that all data in computer are stored as numbers, actually binary numbers. But when you take a look, you might find that it's not what you would expect. Here is a picture. If I open the picture in a classical text editor to reveal its true form, I don't see any numbers, right? The same with the music. This is a sound, actually recording of this video, but where are the numbers? There are some weird characters, half nonsensical. Well, in fact, they are numbers. They are binary numbers, just encoded in different way. Let me show you this. We are going to create a new picture from the scratch and decompose what does it mean when it's saved in this way, what I just showed you. Here is a paint.net. I'm going to create a picture 1 by 1 pixel, as simple as it can be. The color of the pixel will be 1, 2, and 3. Now I'm going to save it. Let me open it. As you can see, I again see some weird characters. What I can do is to switch from this view to something called hexadecimal view, or hex. And now it looks a little bit better. You can already see the numbers on the left side. So each character, in fact, represents a number. We are not using binary numbers in real life in this particular case, because it would be too long. But they are numbers, just coded as hexadecimal. It means that we are using 0, 1, 2, 3, 4 up to 9, as you know, but A, B, C, D, E, and F on top of that. Pretty cool. For instance, number 255. This will be encoded as 8 ones. That's pretty long. Or it can be encoded as FF. Very convenient. And this is what's happening here. I can see my values. 1, 2, 3. Well, the order might be reversed, we are going to talk about it later, but that's it. Now the question is, why this file, saved somewhere in the memory, looks like this and not like a picture? Well, because everything is numbers. It depends on the software what you are going to use to open this file. I need to use software which understands images. It can be whatever, like GIMP or MS Paint, but it must be something specialized. If I open my picture again, I can see that I have my one almost black pixel, exactly as I want. So this is it. Numbers, zeros and ones, represented in hexadecimal form, saved in a file. The place where the file is saved is actual memory. As you know from the previous video, one thing what we used memory for was to save data, as a Jacquard Loom as a first real example. But later on, we added programs as well. Check this simulation from the previous lesson. As you can see here, I have a source code, some sort of assembly code on the left side. I have my memory on the right side, where the memory contains different things. There are registers up there, we are going to talk about them, and the RAM, something labeled RAM on the bottom. You can also see that there are hexadecimal codes 3E, 05, and 3C. These numbers, obviously, are not random. To understand what they mean, you might already guess that because you need to communicate with microprocessor using some specific combination for the commands called opcodes. Actually, this might be it, right? Let's take a look. Here is a table which contains all instructions what our processor can process. Let's start with the first thing. I can see 3E. If I take a look here, 3 and E, I can see MVI, movie immediate. That's exactly what I have here. Second thing is 05. It looks suspiciously like the second argument of the first line. And the last one, 3C, well, it shouldn't be a surprise. It's INR, increment. I wrote a program in assembly language, and assembler translate it to binary form, let's say to machine language, and coded these numbers to a memory, RAM in this case. This concept of saving data and a program, data here represents number 5 where the program is the rest, is known as von Neumann architecture. It is this beautiful design proposed in 1940s. And as you can see, it's nothing crazy. I have my microprocessor, or let's say central processing unit, or CPU, which contains control unit and arithmetic logic unit, abbreviated as ALU. And I have some memory unit which communicates back and forth with those. Also some input device. Output devices is not super interesting for us right now. You might ask if it's not just some historic thing, very obsolete. In fact, it's not. This architecture is used till nowadays. It's a standard in computing. It has been improved, but the basic idea is still there. The last thing which we'll have to talk about is a microprocessor. So next time we are going to talk about it, and we are going to use this picture again. Memory is sort of Excel sheet. Imagine a table with cells where every cell has unique identifier. It's easy as that. The memory can be divided to 3 big subgroups. The first one, the primary memory, is something what you probably imagine as memory very naturally. It can be RAM, random access memory, which you definitely have in your computer or device. We have cache memory, usually L1, L2, L3. They are very fast, very close to processor, and very small. And the last one are registers. Registers are super tiny, but super close to processor for some intermediate communication. So we have register, very small, but very fast. We have cache, slightly bigger, slightly slower, but still pretty fast. And we have RAM, which is the slowest of those 3, but still very fast and the biggest. Common RAM nowadays is about 32 gigabytes. It can be also 16, but it's a pretty huge number in comparison with the others. Secondary memory is something where you store your data. It can be hard drive, HDD, or solid state drive, SSD. It contains various optical disks, CDs, DVDs, Blu-rays, also USB flash drives. Simply memory where you store huge amount of data which is not necessarily needed right now. We continue in our trend. These type of memories are even bigger. It's pretty common to have a hard drive or SSD which has 1 terabyte at least, but obviously they are way slower than your RAM. Just to make it complete, there is also a third group which contains clouds or external hard drives. In general, something what you don't have as a fixed part of your system, but it's there. What might be interesting, the data which are on your hard drive cannot be immediately touched by CPU. They cannot be immediately processed. For that, they must be first uploaded to your RAM. RAM is the place which can be immediately touched by your CPU. And obviously CPU can touch registers and caches as well. It means that it's very crucial to have RAM of a sufficient size. But also it's very important to have RAM which is fast. Size is not everything. You can have plenty of gigabytes, but what is it good for if from your drive to the RAM it will take ages? So no. You need something which is big and something which is fast. And this is exactly what von Neumann proposed. The idea has been expanded. We have a memory, a very big memory as the hard drive or SSD, which stores the data and programs. We have memory a little bit closer to the CPU, to our brain. So we send the data there and the processor can touch it immediately. If processor wants, it can save something to the registers and it can save something to the cache. We don't have direct control over that. That's not 100% true. You can definitely do it as a developer if you are using some low-level language or high-level language, depends on the year. But usually this is not something you care about. And usually you shouldn't care about it. There is a high chance that your operating system and your hardware knows way better what to do than you do. For the end, let me show you something cool. You could probably guess that what it does is to print a message. The message is composed from 2 sentences. And well, there's really nothing special about it, right? Even if you don't know C++, I guess this code is self-explanatory. We have a print something on the screen, and if A is 42, we are going to print something more. Very cool. If I run it, it's gonna look like that. However, let me put a breakpoint here on line 9. Breakpoint means that the program is going to run but stop in this particular place. What I have on the left bottom is memory window. I can literally check my RAM for whatever is there. And on the right side, I have my registers. We are going to talk closer about registers in the next lesson, but for now, let's just say they are pieces of memory very close to CPU, as close as they can be. Let's say that I want to hack, somehow alter this program. I have access to memory, I can do whatever I want, and well, we already know that the program is saved in the RAM, the same as the data, so I can alter the program, right? Even without source code. Well, obviously I can. Here I can switch to disassembly. Disassembly is a feature of Visual Studio which simply take my code and change it to assembly language. Because as you know, I must do it. I must transfer my writing to numbers in the end. And for that I use compiler. If this is confusing to you, you can check my previous video about languages. I can see here in assembly language, if A is equal 42 is decomposed to two instructions. C and P, which is compare, and J and E, which is jump not equal. What the compare does, take whatever is in A and compare it with 2H, which is hexadecimal for 42. It is going to subtract these two numbers, and if the result is 0, it's going to mark it in a special flag. If the result is 0, the numbers I'm comparing are the same. What this instruction does, jump if not equal, is that it checks the flag. If the flag was set, comparison was successful, it continues to next instruction in a sequence, continuation of the printing process where we are going to print the second sentence. If the flag is not set, we are going to jump. And we are going to jump to the address, what you can see here. It's a part of the instruction, it's the first parameter, and well, the address points to the end of the program. So the thing in a branch, the string itself, is not going to be printed, it's going to be skipped. And I can even take this number, I can even take this place in memory and check what's there. It's number 75. It's better to say 75. It's not 75 because we are not in decimal system, so 75. What 75 is, it's definitely some operational code, it's some opcode for instruction. If I'm going to check instructions for x64, I can see that 75 is actually exactly what I would expect it is. Pretty neat. Back to our little hacking. You can see on the right side that one of the registers shines in red. For 64-bit system, this is a register which contains address of the next instruction. You can see that now it points to the line with the yellow arrow. This is exactly the instruction which is going to be run if I just hit run or step. What I want to do is to change this instruction. Let's say that I don't want to print the second sentence, but I have the A42, so how to do it? Well, actually easily. There is jump if not equal instruction, but there is also opposite instruction, jump if equal. If I change this instruction to jump if equal, it should do what I want, right? I can do this, which might look a little bit cryptic, and we are going to talk about this particular thing in the next lesson, but I'm just taking my RIP register and separating the instruction which is going to be processed in the next step. I can see that the instruction is 7575 in hexadecimal, and I happen to know that jump if equal is 74. Let me write 74 with x in front because we are in hexadecimal. And look what happened. I can show you the code. Nothing happened here because the code already doesn't exist. The code has been translated to the machine language, and we extracted the machine language to the assembly language and now playing with that. I'm happy with it right now, so if I just continue to run it, exactly what I would expect happened. Only one thing I can see there is hello there, and the second string has been skipped. That's all for today. I hope you learned something, and see you next time.